Now on this slide you see the two types, so let's say two main strands of systemic risk measurement and modeling summarized. On the left side, the contribution approach, on the right side, the participation approach. Contribution, about the agitation of risk, and the participation about the amplification of risk. So the conceptual distinction between those is we have a systemic resilience to individual failure, whereas the amplification would be the individual resilience to common shocks. Other distinctions are the risk transmission, the risk indicators, and policy objectives. So the risk agitation, so take again the big bang, right, failing. That big bang can contribute to systemic risk on the basis of a few characteristics, by virtue of its size, by virtue of its connectedness, complexity, substitutability, and there are more. This is usually institution to institution. Right? So one institution fails, it has a knock-on effect on another institution, because that bank does a lot of business with another bank. And what we saw from Ramo yesterday when he drew up his networks, right? We saw different configurations of networks attribute varying degrees to this connectedness, substitutability, clearly. So if I have a chain of institutional connectedness, that has a different impact on risk agitation than if I have a circular relationship, or I have a very dispersed network, right, with uniform or very equitable risk weight. The participation approach is different. Right? As I mentioned before here, it's about the institution to the aggregate linkage. So do I hold a large portfolio of certain assets that might be subject to shock? What is my risk-bearing capability overall? The economic significance of asset holdings. So if I experience a massive shock, current FX, foreign exchange, interest rates, asset prices, will my effort to generate liquidity in fire sales cause problems for the system? The main distinction between those approaches is that in terms of agitation, it's about contagion, avoiding so-called moral hazard. So big firms causing massive problems. When I say big, I mean big as a catch-all for those properties. A firm doesn't necessarily have to be big to be systemically relevant. Give an example, that there are banks in almost all jurisdictions I've looked at in the context of my fund work that are smaller than the biggest banks, but because they're so connected or they have a particular function within the system to become systemically relevant. I don't need to name names, but we know certain banks are very heavily engaged in brokerage activity, or very heavily engaged in underwriting. So when I say size, I don't mean size necessarily signifying the balance sheet size, but size as a catch-all for those properties. On the right side, the policy objective would be maintaining the overall functioning of the system, maximizing survivorship, and preserve a collective burden-sharing system. So, for instance, making sure that our deposit insurance scheme still works and is suitably funded to absorb a shock of institutional failure. Because, give an example, if again this big bank, right, fails, that failure might cause another bank to fail, but it also might bring down the deposit insurance scheme, right? Some of you who followed the crisis, if you might have also read articles about the FDIC's, the Federal Deposit Insurance Corporation, that's a deposit insurance in the United States, that their funds have been heavily depleted by small bank failures. So this is not entirely hypothetical, but a reality. So we get the definitions out of the way. Briefly, on systemic risk measurement, there are a few challenges, and I've listed some, and clearly that I have no claim to comprehensiveness here. What are the challenges that we face when we model and measure systemic risk? First of all, we have an identification problem. Distinguishing causes and symptoms. What's really the underlying cause of a certain characteristic we identify, we measure, we try to model? What are the subjects? What are the objects? And the state contingency of data and information. Things change all the time. How can we reasonably model such state contingency? The diverse nature of extreme shocks complicates the coherent and reliable measurement of systemic risk. Well, that's really a catch-all to identify, to describe that this is the immeasurable, the black swan, the unanticipated risk, the extreme, the unknown. The limited usefulness of certain quantitative measures. Many quantitative measures are designed to measure something that's very unusual, outside robust statistics. But by being outside robust statistics, the models themselves might invalidate themselves in case of a shock, an extreme shock. So the more we try to measure, the more we try to optimize, we might be doing something terribly wrong. So in our world of trying to create comfort in numbers, we might suffer from another problem, which is the God's complex. The God's complex is that by seeking comfort in a huge number, a huge amount of data, we believe that we know it all, that our model has delivered the incontrovertible truth. And that might not necessarily be the case, because we haven't even, if you explore further, scratched the surface of what's available in terms of information. So the desire to get as much data as possible and to optimize an existing model might create wrong comfort, misguided comfort in the validity of our claim. Complex modeling risks losing transparency and highly dependent assumptions. We had a very heated exchange yesterday in one session, I believe, or one presentation about them on time series econometrics. And this is when the theoretical and the practical side of things clash. Some things might be just too complicated, too complex to implement for the purpose and the task at hand. And some things can be transposed in reality, and some things cannot. And some things cannot because we lack the computational power, we lack the institutions, but also we're human after all, and our brain can only hold so much. So that is an issue. And then finally, as I mentioned before, danger of underestimating practical problems. Yeah. So it might be a nice paper, it might be a nice model, but the practical reality looks different. On just a few principles, and as mentioned before, we don't have a catalog of properties of systemic risk measures, but if you read systemic risk papers and follow the literature over the last few years very closely, one can certainly extract a few properties. Some of them are plurality. We also touched upon that in the regulatory session yesterday, is you want to create an ecosystem of challenge. I believe challenge sums it up. you always want to be vigilant and mindful that the model could be wrong. It might not be wrong today, but it could be wrong tomorrow when it matters. Accuracy versus timeliness. The closer I get to a shock event, the more accurate my model. The farther I'm away, the more inaccurate I am, but the more time I have to act. So we're always torn, especially in the practical side. I also worked in industry many years ago, is how good is a model? It's very accurate, but I have no time to act. At the same time, how good is a model that is very, should I say, less accurate, but I have plenty of time to act. So I want to strike a balance. Completeness of risk measure. So you also want the risk measure to be reasonably complete and coherent. And I'll talk about that more, but for the sake of time, I'll just go over that quickly. And then very important, and that's frequently forgotten, is external and business environment mitigating factors need to be taken into account. So while on the surface, certain things look the way they are, they might be very troubling, they might cause a concern, they might create an expected shortfall measure which attributes systemic relevance. There are mitigants in place. Businesses don't face disaster without action. Businesses will act, whether they act prudently or not, whether they act consistent with our rational expectations or not, whether actions can avoid market failure or not, it's a different matter. But as a matter of practical reality, is that the business environment does matter, and the ecosystem, how it functions, does matter. And the past might give us some clues about how an ecosystem might evolve over time. So our models have to take that into account. Right. How are we doing on time? Oh, good. Developing risk measures. First of all, we need to be, we have to develop a measure of dependence in some way. And there are various approaches, and I just want to pick upon one particular one, very simple. And for some, well, most of you, it's probably common knowledge already. But for some of you, it might not. So let me just go over it quickly. So when we talk about systemic risk, we imply already some concept of dependence. One risk factor causing another risk factor or several other risk factors to change. And that change is dependent. And I need to have a sound grasp of that dependent structure. Then I can model it parametrically, non-parametrically, various approaches. So, for systemic risk, the task at hand is quantifying possible multivariate linkages, and the objective here is to account for the probability of large joint outcomes. And since we are most concerned about joint negative outcomes, joint negative adverse events, that is the focus of our research. However, we need to acknowledge that shocks follow a dynamic process, and that small shocks might be transmitted differently than large shocks. So there is the severity of shock might impact the measure of dependence. Now this is very important because what I'm going to explain in a second relates exactly to that point. The challenge is that standard econometric techniques don't acknowledge this objective. They're seriously misleading in the presence of heavy tails, non-normality, we have an infinite mean, high volatility, or as in cases where the second moment is not defined, and then nonlinear changes of asset values. I'll give you a very practical example. So that's just that's correlation, yeah? So we're all familiar with that. So we have the covariance normalized by the standard deviations of series x and y. Right? Simple correlation. What correlation does not do, it does not take into account non-normality and non-linearity. Correlation is only sufficient if we have a joint probability distribution that's elliptical. However, in reality, that's hardly the case, right? As we know. We have joint extremes, right? That's why we use copulus. That's because other sorts of techniques to understand, you know, how the behavior in the tails is different. Also, maybe as a point of note here for some of you, normal distributed random variables going to generate jointly normally distributed outcomes. So you have two normal distributions that generate tails. Yeah? What are alternatives to correlation measure of dependence? We've got several, and I've grouped them based on the shortcomings of correlation. Which particular shortcoming do they address? So we have rank correlation, quantile regression, conditional correlation, dynamic conditional correlation, DCC Garch, Engel, Robert Engel, for the infinite volatility shortcoming of correlation. We have nonlinearity. For nonlinearity, we can use entropy. Entropy measure has been quite popular. And for heavy tails, we've got copulars, chi-statistic, non-parametric approaches, and then we also have extreme value dependence. Right? And one, I will hope to have time, introduce multivariate generalized extreme value theory. But there's still, of course, the unresolved issue is how do we get robustness for models that measure things that don't occur very frequently, thanks God. So briefly, and I'll skip over it quickly, that's a known measure. I added a few bells and whistles, but we can develop a simple quantile dependent measure of dependence bivariate between two vectors, right? As a chi-statistic, and the defined the presentation will also be available, I suppose, later on. These are the two measures, but what this basically describes is gives me a measure of dependence, much like correlation, but I can control for the magnitude of shock or the degree of change. This way, I have a correlation, in inverted commas, that is sensitive to the magnitude of joint change. So I can distinguish between a small joint change and a large joint change. So if to illustrate that, correlation assumes constant dependence. So on this chart, you see here, we have the measure of dependence in percent on the y-axis, and then we see here the change in equity prices. And that shows the Dow Jones and FTSE 100. And that was over a time period since the start of the financial crisis. The correlation between the two markets is 58%. Now, correlation doesn't distinguish for periods where the equity price, the joint change in equity prices in both markets was small, was large. It doesn't distinguish between the magnitude of joint price changes if that's assumed a distribution. So here, if I look at joint positive changes, so both markets increasing tremendously, or both markets losing variation in inordinate amounts. However, if I apply a chi-statistic, I can get a measure of dependence that is sensitive to the equity price change, the joint equity price change we see in both markets. If you focus just on the blue line now, the blue line shows me that for large positive changes in both markets, the dependence is 35% only. Whereas for very large joint negative changes, so both markets losing market capitalization, the dependence is 75%. And again, contrast that to correlation, which is agnostic to the magnitude of change I'm measuring. Now, to the property of state contingency, look at the red line. The red line calculates the same measure, but it does so after Lehman. So the blue line is before Lehman collapse. The red line is after Lehman collapse. You see how the dependence actually changed. So we see an upward shift in the dependence structure, indicating, at least based on that measure, that the overall transmission dependence between both markets across the board has increased. As people that are concerned with systemic risk, we are interested in that side, the red part, large joint negative outcomes. And you see here the dependence for joint negative outcomes, for joint negative changes in market capitalization has reached 80%. So that's an important observation. And of course, this is just for the one-shot result for one period. We can also look at a particular percentile of our CDF and focus, let's say, on the lowest decile, the one I'm most concerned about, the largest joint negative changes, and track that over time. How did the extreme or the tail change over time between the two markets? On a very simple measure. And if you do that, then I get a surface, right? So I get this is what we had before on the x-axis, right? Now we have time, and we have the y-axis, the dependence. So see how, over time, starting July 2007, using, if you recall, basically we looked at it just before, we looked at it from this way. Now we roll that forward over a time window with updating, and see how that changed, and how that peak over there at the top has come about, right? So overall, we see that there is very low contagion, or I should say spillover, rather. There's low spillover for positive outcomes, but there's increasing spillover risk for very negative joint outcomes. Now, of course, this is very accurate, and this is more catered to policy rather than market behavior. Right? If I were a trader, this might be good background, but it doesn't help me necessarily. But what does help me as a policymaker is to understand and appreciate that these markets have become closer connected. That might be because of perfectly natural, perfectly explainable behavior, but also might be true to the fact that now the market microstructure has changed to an extent that is different from the past.